Welcome to another podcast. In this episode, we're going to be comparing and contrasting lists and sets. And while the two topics are related, they are very different in application. We're going to be considering all throughout the coming weeks how to count problems involving both lists and sets. It turns out to be a major component of sort of the foundations of mathematics to be able to count both. And we're going to start, I'm just going to divide the screen sort of into two somewhat equal parts here. And we're going to start by looking at lists first. So let's consider first what a list is. The easiest description that I can give is by showing you an example. So an example of a list is something like the elements 1, 2, 3. Also, they don't have to be numbers, so lists can contain anything. So here I'm just going to give you some random elements. Lists can have variable size, so we'll talk about all of that. But these are just two examples of lists. Notice that the elements are grouped inside parentheses. That's going to be important when we compare it to sets here in a second. So sort of the first property of lists that I want to talk about is that the order matters when it comes to a list. Essentially, if you switch the order, you get a different list. So the elements 1, 2, 3, that list is not equal to the list 1, 3, 2. Those are in fact two different things. Two lists are equal to each other if they have the same length and the exact same elements in each spot. So they're basically duplicates of one another. The other thing here that may or may not be obvious is that the length of a list matters. There's a couple of different ways that you can maybe go about saying that, but I just want to talk about some names that we give for lengths of certain lists. So for example, if you have a list of two elements, in math we typically call that an ordered pair. So the order part comes from the order mattering, and then the pair part obviously comes from there being two. If there's three things, then you will oftentimes hear the phrase ordered triple. And suppose there are n objects, and so I'll write this using numbers to designate the slots, but suppose there are n objects, you'll hear the term n-tuple oftentimes given. So an n-tuple, a 2-tuple would be an ordered pair, a 3-tuple would be an ordered triple, and in general if you have n objects it's called an n-tuple. The name given to lists, sometimes they're also called strings as well, and then sometimes they're even called permutations. Although we're going to avoid the term permutations in this course because from an abstract algebra setting, the term permutations has a little bit of a different connotation. So we're going to try to avoid that term this semester. Think of it as lists and strings. Now, the third sort of thing that I want to look at with you is that the elements of a list can be generated from any set. So the elements come from sets. So in some sense, lists are products of sets, and we'll look at how that comes about here in a second. So sort of the fourth thing I want to talk about is how you figure out the number of ways to create a set. So basically, if a list has n elements, meaning it's an n-tuple, so if you have an n-tuple, and each slot of the list can be filled with, I'll say M1, M2, all the way up to Mn objects, I guess is the best word. So basically think of the list as each slot of the list you have M1 total objects, M2, Mn, where obviously M1, M2, Mn are natural numbers, so you could fill it with 0 objects, for example, but that would be kind of silly because then you wouldn't be able to create a list if you couldn't fill one of the holes. So really when we think of M1, M2, and Mn, these are positive integers. So positive integer number of objects, then what we say is the total number of lists that can be created from this setup is equal to the product, and this is some new notation I think for a lot of you. It's the product over all possible values. So it's M1, so this is just shorthand notation for M1 times M2 times all of them multiplied together. Basically it says the size or the number of possible lists that can be generated is dependent on the length of the list and the number of objects that go into each slot. Putting it all together, when you come up with this total is something known as the multiplication rule. And in a future video, we're actually going to apply the multiplication rule to look at a couple of different examples. But for now, this is what I want you to think of. The total number of lists that can be generated from M1 through Mn objects in each slot is the product of the number of choices for each slot. That's basically how you should think of it. Alright, let's sort of shift our focus now to sets. So if I consider just sort of some basic things involving sets, the first thing is the notation is very different. We use usually curly braces. So here's an example of a set. I could also have a set involving numbers or elements or whatever the case may be. And in this particular case, order does not matter. Which is basically saying that the set 1, 2, 3 and the set 1, 3, 2 are equal to each other. Now, this implies a couple of things about what it means for sets to be equal, and we'll talk about that as we go through. I also want to point out that just some notation that we use. We say that the element A is a member of, and let me just give this set the name S. We say that A is an element of the set S. So this little sideways E pitchfork looking thing, this is called inclusion. Includes or inclusion is an element of. That's how you should read it. Alright, so the order of a set doesn't matter. Sort of the second point that we have here is that repetition doesn't matter. In other words, repetition doesn't count. Let me just put it that way. And what I mean by that is the set 1, 1, 2 is the same as the set 1, 2. Because all a set cares about is what the elements are, not how many of them there are, and in what order they're. And order doesn't matter here, and repetition doesn't matter here. So the set 1, 2 contains the elements 1 and 2. The set 1, 1, 2 contains the elements 1 and 2. Therefore, they are the same set because they contain the same elements. The third thing that we look at here is the length of a set. Because we talked about lengths of lists, lengths of a set is really more the size of a set. So the size of a set has a special notation. The size of a set is based on the number of elements in the set. And suppose that you have a set S consisting of the elements 1, 2, and 3. The notation that we use for the size of the set is this bracket notation called the cardinality. So this is called the cardinality of the set. It has 3 elements, therefore its size is 3, but we use this fancy term called cardinality to basically mean size. It's an older term, but you still hear it in a lot of literature today. Sort of the fourth thing here that I want to talk about is a relationship between these two objects. So we were talking about lengths of lists. Now I want to talk about how sets generate lists. So suppose that we have finite sets, meaning they have a finite cardinality. So suppose we have finite sets S1, S2, all the way up through Sn. Then a list can be formed from these sets via the operation known as a Cartesian product. Now, the notation here is pretty standard, so let me just explain what the Cartesian product is. The Cartesian product is, let's say, S1 cross, and you say cross, you don't say times. S1 cross S2 cross S3 cross all the way up to Sn is the set of n-tuples that can be formed from taking elements from S. In other words, each of these SIs is an element of the larger set SI that it came from. So for example, S1 is an element of the set capital S1. S2 is an element of the set capital S2. Basically, you could think of this operation, which is called the Cartesian product, you could think of this operation as matching elements from the n sets and putting them into a list. So that particular operation is a very important operation in the sense that it generates a list, and we know using multiplication rule how to find the total length of a list. So sort of the next thing that you would talk about then is the length of this list. Well, not the length, that's not what I mean. I mean the number of possible lists, which is the size of the Cartesian product. Is given by the multiplication rule. Because the Cartesian product is the set of all possible lists that can be formed, and we know the set of all possible lists that can be formed is found by figuring out how many things can go into each slot. Well, if you look at S1, how many things can go into the slot for S1? Well, there's as many S1s as there are in the bigger set S1. It's however many elements S1 has. So basically this is saying the size of the product is equal to the size of the individual sets. So if I multiply the cardinalities of each set, then I get what is called the product rule or the multiplication rule. So a lot of times they'll call this the product rule because we're talking about set products here, but it's the same as the multiplication rule over here. In other words, these two things are completely analogous and they come from the same place, but the notation is a little bit different. So just understand that lists are formed by plugging in objects from sets into those lists, and then you count the list, or you count the Cartesian product, or you count the set that's formed by figuring out how many objects come from each set and then multiplying them all together. So this is called the multiplication rule. There's a little bit of difference here in the terminology, but I wanted you to see sort of the two things laid out side by side so we can get a handle on some of the notations. Thank you for watching.